So in SCSI, a SCSI command is basically you send a command to a target transfers some data, and then it transfers the status. That's a SCSI command. A SCSI command translates on fiber channel side to a exchange. In fiber channel side, the terminology which is used for this whole transaction is called an exchange. A command on SCSI side involves phases. There is a command phase where the initiator says, I want to read some data. And there is a data phase where the target transfers data, and there's a status phase. So a command consists of phases. Similarly, on fiber channel side, an exchange consists of sequences. And beyond that, there is no further delineation on the SCSI side, but on fiber channel side, a sequence consists of frames. A fiber channel frame then further consists of something called fiber channel ordered sets. So an ordered set is a 40-byte transmission word. Sorry, 40-bit transmission word. And on fiber channel wire, 10 bits is 1 byte. So they do 8-bit, 10-bit encoding. So a 40-bit transmission word is actually 4 bytes. So everything is transmitted in 4-byte chunks. And the minimum transmission which happens in a SCSI, for SCSI commands or normal I/O is a frame. And a frame can be from 0 to 2112 bytes in chunks of 4 bytes. And frames connect together to form sequences. And sequences connect together to form exchanges. And similarly, when a initiator says, I want to do a read, or I want to do a write, or I want to do any other SCSI command, it initiates an exchange. And that exchange then is carried out. So the initiator will send a command to the target. That will be one sequence. The target will then start transferring data. That will be another sequence. The entire data transfer is another sequence. That sequence may have one frame or more than one frames. Similarly, then the target will say, I want to transfer status, and that status will be another sequence. That most of the time, status sequence will have only one frame. So if I look at a SCSI transaction, it will be, so here is initiator, here is target, and this is, let's say, one frame. So the initiator sends a SCSI command to the target, right? The target transfers data, which is multiple frames, to the initiator, and then the target transfers status, which is another sequence. This is command. So this is, let's say, sequence number 1. This is sequence number 2. And this is sequence number 3. All these 3 sequences form one exchange.
A question. How is with SCSI, the concept of a disconnect, reconnect actually mapped to this? Does it come back as a separate exchange on fiber channel, or is it still using the same exchange?
There's no concept of disconnect. The disconnect itself does not exist. The reason disconnect existed in SCSI was because you had to hold the bus.
Cable. Yeah.
Right?
Okay.
So here you don't have to share the cable. You
Okay.
don't have to hold the bus. So there is no disconnect
Okay.
concept. So with this, what they did in fiber channel was, so every exchange has an exchange identifier, has a number which says this number represents this exchange. Every sequence has an identifier which says, this is sequence number this. Within a sequence, so there is a sequence ID, there is an exchange identifier, there is a sequence identifier. Within sequence, you can have multiple frames, which is basically a sequence number. So all this information, sequence number, sequence ID, and exchange ID, are part of the frame. So every frame which goes on the wire has all this information. And the benefit is that makes fiber channel hardware routable. So A hardware engine or a switch can look at a fiber channel frame, and it has all the information about that frame without actually having to maintain any context of who sent what in where. This is different from networking, where in networking, connections are maintained at TCP level, and devices like switches have to actually keep that knowledge around that there was a connection made at a TCP level, and then it has to track frames. In fiber channel, all this information is part of every frame which goes on the wire. So, so this is a basic transmission word, which I said ordered set, which is 40 bits. And a ordered set, so there are frames which go on the wire. At the same time, there's some communication which happens between two nodes at the fiber channel level. So ordered sets are also used for that purpose, and that's what this slide is about. But we'll go to the next slide, which talks about frames. So this is basically a fiber channel frame. And you can see it has a frame header, which has destination address, source address, where it is coming from, where it is going to, some control information. And then it has something called sequence ID. So this basically tells which sequence within that frame this frame belongs to. Which sequence within the exchange this frame belongs to. Similarly, there's a sequence count, which tells within this sequence what is the number of this frame. And then there is so this is an originator exchange ID, and this slide is actually not correct. This is RX ID, this is responder exchange ID. So both initiator and target track exchanges in terms of exchange identifiers. So the guy who starts an exchange is called an originator, the guy who responds is called a responder. So both of them maintain exchange IDs. The point I'm trying to make here is that all this information is actually part of the frame, which means that you can just look at the frame. You don't need to actually track a transaction. You can just look at the frame and figure out which transaction this frame belongs to. Go to the next slide. So we talked about ordered set. We talked about fiber channel frame. So the difference between ordered set and a frame is that an ordered sets make up, multiple ordered sets combined together make up a frame. And fiber channel sequence is basically a series of frames which belong to the same sequence. Fiber channel exchange is basically a series of sequences, and we did a comparison with the SCSI command, where exchange is basically a complete SCSI command, the sequences were part of the command, and a frame is one unit of a sequence. Okay, so with that, we'll dive into the fiber channel number game. So this is the most confusing part. At least a lot of people have asked me these questions about, what all are these numbers? And I'll try to describe all of them, and it's kind of confusing, but we'll see where it goes. So the basic thing is there is a need for a device identifier. You have a device which you need to talk to, and there's a need for an address, for an identifier for that device. In parallel SCSI days, there was a SCSI ID. You set a jumper on the device, and that jumper basically said that's the identifier. In fiber channel arbitrated loop case, there was something called port addresses, which were used to address the port. So there's another question is why there was 126 devices on fiber channel? Why not 256? Because addressing is 8-bit wide. So the problem is there is something called running disparity. And this is, I'll try to explain as best as I can. So every time one device on a loop wants to talk to another device, it has to send something called arbitration, ARB. And ARB is an ordered set, which means it's 40 bits, which means it's 4 bytes. The problem with 8-bit, 10-bit encoding is that you have to maintain something called running disparity. A disparity is basically difference between number of ones you transmit and number of zeros you transmit. If you transmit too many ones, all of a sudden the wire will be positively charged. And the next zero you transmit will be consumed by the wire itself. It will not go to the other end. Similarly, if you transmit too many zeros, the wire will be negatively charged. And the next one will be consumed by the wire itself. So you have to keep a balance between number of ones and number of zeros you transmit. So every encoded word, every 8-bit to 10-bit encoded word had two disparities, a positive disparity and a negative disparity. If the wire is too positively charged, you send a word with negative disparity. So basically, the whole idea is to maintain the charge on the wire. And the way the arbitration ordered set was designed, so the arbitration ordered set has a command, which is an arb command. And then this was not used. And this was the source who sent it, and this was the destination, who is the receiving end of it. So the way this was designed, you could not use all the 256 combinations here. If you use that, then disparity will be either too positive or too negative. So that's why they came up with the combinations which can be used. And those combinations turned out to be 127. So one is obviously reserved for the switch to do something called public loop. And I won't go into detail of that. So the remaining one left is 126. So that's why it's 126.
And that's why there's that translation table too?
Yes, that's why there's a alpha to loop ID translation table.
Any hardware engineers in the room? Great. This is why I hate hardware. I don't much care for hardware. It's just that nasty stuff that makes my software run fast. I mean, to have to worry about positive and negative charged wires in the software side.
But you see, I'm just trying to see where the protocol came from, right?
No, it makes a lot of sense in a weird hardware-centric sort of way.
Yeah.
I have a quick question for that new copper fiber channel that you had mentioned before.
XTBSD?
Yeah, will that still be a problem with the negative positive charge?
Yeah, I mean, I think this is the problem with the 8-bit, 10-bit encoding. It doesn't really matter how it is used. Because even if you use it for optical, at some point there is a transceiver which is converting copper signals to optical signals. The problem still exists at the transceiver level.
Sounds like a bug to me.
Yeah, we'll fix it. So yeah, this is the table which Chris was talking about, translation of loop ID to alpha. So a loop ID is really a linear number from 0 to 127. But as I said, if this is a table of all the 256 numbers, we could not use all the numbers. So they used some numbers, and they did not use some other numbers. So you had to kind of translate a linear address from 0 to 127 into a nonlinear address. And so these nonlinear addresses are called alphas, arbitrated loop port addresses. And these linear addresses are called loop IDs. So you have to keep translating between loop IDs and alphas, and that's where this translation table comes from. So that's the fiber channels, loop ID and alpha. There's another number which is very commonly used is the worldwide name. The worldwide name, as I described, you can relate it to networking. It's basically like the MAC address on the Ethernet card. It's a 64-bit number, which is uniquely identified and assigned to every fiber channel device.
Now, on a local loop, the loop ID then also becomes the target property, right?
In some cases, not all the cases. So I can go into detail of that. Basically, if we are able to acquire the hot address, if we are able to acquire the hot address, then it becomes the target
If you have
address.
a target, that's where it came from, as opposed to WWN addressing.
The WWN addressing comes into play when we are not able to acquire the hardware
Right.
address. So then we use WWN as the target identifier. If we are able to acquire the hardware address, let's actually go into that. Let me go into that's actually an